Good evening, folks. This is the video on negative binomial regression. I apologize for just getting this up as I've spoken to some of you over the last week or so. Finding time to do the video is pretty tough considering the kids are home. So, like right now, it's going on midnight right now. So, this is pretty much the time that I have to do it. So, I'm gonna get these out much quicker. You do have my word on that one. So, hopefully, everything is clear in this video, and I'll set up some time in a chat fashion for us to be able to talk if you have any questions, concerns, or if you want to follow up on any of the things that I want to go over. I'm also not going to have this as long as the last one. The last one was longer only because, we were going over a significant number of the regression assumptions and the charts and the plots and everything else in there. It took some time. So this one is not going to be even close to that amount of time of that video. That being said, a negative binomial regression is what we're going to talk about for this video. A Poisson is also another count model. I'm skipping over that one, and I'll actually tell you why here within the next few minutes, because it really, to some extent, really doesn't make sense to actually do. So first, let's talk about what a count model is. If your outcome of your model is a count model, then you have to figure out what's the appropriate count model to actually do. There are several count models that we're going to talk about. We're going to talk about negative binomial. We're going to talk about zero truncated. We're going to talk about zero inflated, negative binomial. There are multiple count models. So depending on how your count model is measured and the assumptions that go in there, that's going to determine the type of count model that you run. I will focus tonight on negative binomial, and I'll tell you for the next video the different type of conditions and assumptions that go into each count model. But for right now, a negative binomial regression is what we're going to go over. So now that we briefly discussed that, let's talk about what a count model is. Does anyone have any idea? Okay, clearly nobody's going to raise their hand since this is a recorded video, but I figured I'll insert a little bit of laughter in here. I'm not sure if you laughed or not, but I found it kind of funny. So the account measure is when your factor is a non-negative whole number. And zero can be included here. So a non-negative whole number, and again, zero can be included. So for instance, examples can be the amount of money that somebody makes if you round it to a whole number. If you look at the number of times somebody was arrested, the number of countries with democracies across the world, the number of people who are infected with COVID-19, the number of TVs people have in their home. So all of those are whole numbers. Zero can be included, and it cannot take on a negative value. So that's what account value is. Oftentimes what people do is they use an ordinary least squares regression to analyze count measures, and that's not the appropriate thing to do. Often there actually is some research that suggests that when you try to use a OLS regression to analyze a count measure, the fit of the model is not as good at all. So first, let's talk about, just broadly speaking, what is a count model and why ordinary least squares regression is not the best way to analyze the data with that type of outcome. Because most times you'll have a distribution that is skewed. You won't find many count models out there where the distribution is a normal distribution. And we talked about the distribution of normality with the residuals and everything else in the last video, so I'm not going to go over that again. But most times you'll find a distribution that is very skewed, which means they don't meet that assumption. Oftentimes what people do in order to run an ordinary least squares regression, what they end up doing is trying to transform the data in some way to meet that normality assumption of ordinary least squares regression. That's not the appropriate way to do things, because it's taking there's already a model, there's already statistics to analyze a model that has these count outcomes. Why then mess with the data and transform the data and do all these different things if you already have statistics that can analyze the outcome, analyze the model as is? And again, once you start messing around and transforming these outcomes, is not in the original unit at that point. It just does all types of concerns. It's a common way to do things, but it's not the appropriate way to do things. So often what people do to make a count model a normal, or have it approach a normal distribution, that they take the natural log of the outcome. And transforming the outcome, you're doing the same thing to each value. So technically the integrity is still there. You're just changing the unit of the outcome. As an example, just to make it easy, let's say you're looking at somebody's age in years. If somebody's age 1, if you measure it in years, the value is 1. If you measure it in days, the value is 365. If you measure it in months, the value is 12. Same thing, but the unit is different. That's what a natural log is. You're just changing the unit of how you're measuring that outcome, and you're taking the natural log, so it's just a different unit of the number. So that's all it is. But you're still messing with it, and you really don't need to. Trying to make it fit a distribution that it really wasn't meant to fit. So doing that is not necessarily the most appropriate thing. Also, why ordinary least squares regression isn't typically appropriate for a count model is typically with count models, 0 is a common value that's included in there. So in terms of the values within the outcome, 0 is typically a pretty common value. For instance, if you look at the number of times somebody was arrested, most people have not been arrested. So 0 appears in the data set, would appear in the data set a lot. You cannot take now 0 does not have a natural log. So if you try to take the natural log of 0, an error would appear. So oftentimes what people do, they add a value to every score within the data set. So they would add maybe 0.1. So all the zeros would end up being 0.1. All of the 1s will end up being 1.1. All of the 2s will end up being 2.1. All the 3s will be 3.1, and so on. So you'll add the same value to everything included in the data, and then they'll take the natural log from that. Because anything other than 0 can have a natural log, so they'll typically add a value so the zeros can be included. So you see what I mean about all of these different things you have to do in order to make a count model work. You may have to add some values to it that don't exist. Then you're changing the unit, and there it just becomes a complication. So for that reason, um, it's just honestly not a good idea. It's a common thing that folks do, and you'll see it done a lot. And some of the research you're looking at, even for this class, for your paper, you might see it being done a lot, but it's not the appropriate way to do things. So that's what a count model is, and why ordinary least squares is not the appropriate statistic to use to analyze count outcomes. So let's go through a negative binomial regression first and talk about a few things. So for this, use the Jordan data that we have for class that's in Blackboard. I have the do file here for me. So just go to Blackboard and download the data set, and here is the data. So you'll see that some of the file extension is different because I used this another time that I taught this class, not at AU, but when I was at UMass Lowell for a PhD course. So that's why you'll see it looks different, but the data is the exact same. So just use the Jordan data. So the outcome we're going to look at is the number of rearrests. So which is over here, NUMREARR. So that's going to be outcome. Looking at the number of times defendants in this data were rearrested. So that's what we're going to look at. That's going to be what we're going to look at. So it's a count model. It'll go from 0 to whatever. Nobody can be arrested a negative number of times. So, so it's by definition a count model. So whole numbers and everything. So first, let's actually take a look at the outcome. So let's take a look at it. So first, we're going to do a histogram. Now, let me explain what this syntax is, because it's a little different from what we've been doing in this class. So I'm doing a histogram for the number of rearrests, which is this, and I have if. So if you're not familiar with the if function in Stata, you should learn it. So we're going to analyze a subset of the data. So if I'm looking at rearrests, not everybody was released. Not everybody was released from jail, or released pre-trial, not jail. So not everybody was released before they went to trial. So release equals 1. So this is equals. So in Stata, if you're talking about a value equals if you're looking at a subset that equal a particular, a value, you got to use the equal sign twice. So release equals 1. So we're looking at those who were released, because 1 means they were released, 0 means they were not released. So if I'm looking at the number of rearrests, I only want to look at people who were released. So the number of rearrests, if they were released and their time at risk is greater than 0. So time at risk just means the time that they were on the street, the time that they actually had the ability to get rearrested. So so that's what time at risk means. So time at risk greater than 0, because I want them to have had some time to actually have been rearrested. So histogram, number of rearrests. If I wasn't looking at a subset of the data, then none of this would be here. The if function, it would not be here. It would just be histogram, number of rearrest, and that's it. But I'm looking at a subset. So if they were released and they actually were on the street, they actually had time on the street to actually engage, to actually get rearrested. Greater than zero, and that's looked at in terms of the number of days. So, hope that makes sense. So, if you then hit return, this gives you a picture of how that outcome looks. As you can see, over 30, maybe 34, 35% of the people had zero, were not rearrested at all. And if you put if you put a distribution around this and actually looked at the normality of it, it wouldn't be normal because it goes pretty much from here up and then it goes down, and it's very skewed. This is how most of our data look. In the social science field, most of our data looks like this. So this would not meet that normality assumption of ordinary least squares regression. It would not. So again, what some people try to do, they'll start trying to add numbers and taking the natural log of this and everything else. And, there's no need. There's absolutely no need. So this is how the distribution looks. It doesn't meet the normality assumption. So linear regression cannot be used. Second, so if those of you who have some understanding of count models, you might be asking me, why don't we use a Poisson model? Which Poisson and negative binomial regression are very, very, very close friends. They're very close friends with each other. So what distinguishes the two is the relationship, or the values of the variance and the mean. If the variance and the mean are equal to each other, you can use a Poisson. If the variance is greater than the mean, you would use a negative binomial regression. Very rarely will you find that the variance and mean are equal, and that's just reality. That truly is just reality. The variance and the means very rarely equal one another because you typically have a distribution that looks like this, where you have a whole lot of people who are close to the bottom, and you have your more extremes at the top, and the variance typically is pretty large. So, but we can test to see whether or not the variance equals the mean. So if you put in some number of rearrests, comma, detail, and I'll tell you why to put the detail function if you choose. Then if, the same, making sure we're looking at the same subset of data, release equals 1 and rest time is greater than 0. If you do that, you will get some descriptives for number of rearrests. So what we really care about is over here. So you see there's 208 once we looked at the subset. The mean is 2.375. And you see that the variance equals 11.38527. The variance is much more than the mean of 2.375. So a Poisson regression would not be the appropriate statistic to use. Again, in all of my years of research, I have not seen, for any social science research that I have been a part of, I'm not saying it does not exist, I'm sure it does exist out there somewhere, but for most of our work, not just my work, our work, you will not find where the variance equals the mean. So to me, going over Poisson really is pointless to some extent. Um, but if by chance you find data out there where it does support it, you'll do it the same way. You'll just change the command from negative binomial to Poisson, and the same interpretations. All of those things are still there. The interpretations of a negative binomial and a Poisson are the exact same. Exact same. So, so that's one way to look at the variance and the mean. Another way to look at it, if you don't want, for whatever reason, don't want to look at all of these different numbers and values and everything else, you could just take the detail function off. So the detail will give you the variance itself. If you take the detail off, so just sum, the number of rearrests, and the if function, so there's no detail in there. This is not contained down here. Then you'll see the mean of 2.375, the standard deviation 3.37, and the variance is the standard deviation square. So if you square 3.37 4206, you'll get the variance, which is 11.38527. So clearly here, the standard deviation is more than the mean. So clearly, if you square it, it's going to be much greater than the mean anyway. So this will give you a good idea whether or not you can use a Poisson or negative binomial. So here, the variance exceeds the mean, so we cannot do a Poisson. So we do a negative binomial regression, because the assumption of Poisson is that the variance and the mean are equal. So a negative binomial relaxes that assumption, and it allows the variance to differ. It allows the variance in the model to not be equal, to be different, to be greater than the mean. So again, most people do negative binomials because, again, just the rarity there. So that's what you should do first to test to see whether or not you should do a Poisson or negative binomial. So make sure you check the variance and mean first, so you'll know which statistic to actually run. Make sense? Any questions? Seeing no hands? So then I'll move on. Okay. So here is the syntax for a negative binomial regression. Negative binomial regression, NB for negative binomial, and REG for regression. Negative binomial regression. Then you have your outcome, number of rearrest. The predictors we're going to put in the model are age, gender, convicted, and this is whether or not the defendant was convicted, and again, are looking at our subset if they were released and risk time is greater than 0. So negative binomial regression, the outcome, number of rearrests. So you're looking again, the predictors of rearrests for defendants. And the predictors in the model: age, gender, and conviction. So remember to indicate these are categorical. Got the I dot. Because these are dummy predictors, they're not needed, but it's easier if you're going to do some predictions later to have the I dots there. But as you know, these are not required. So the enter. So here is the model. And you'll see that it fitted a Poisson model, constant only model. I'll tell you what those things here mean in a second. Um, so a lot of this output should look familiar to you. Number of observations, 208. Um, all of the likelihood ratio chi-square and the probability chi-square goes hand in hand. Remember, the likelihood ratio chi-square is testing whether or not all of the predictors are equal to 0 in the model. If all the predictors are equal to 0, then this would not be significant. So the likelihood ratio chi-square is 22. It is significant, so which tells you at least one of your predictors are not equal to 0 in the model. The pseudo R square, again, if you move the decimal place over, that's just telling you that this model, in terms of looking at rearrest, is explaining about 2.67% of rearrest. Oh, one thing I forgot to tell you. So then we'll go back. So if you're looking at, if you go back up and you're looking at the descriptives here, you see that the lowest value in the data is 0, meaning people were arrested. You know, the lowest value was 0 times, and the maximum number times somebody was rearrested was 23 times. Apparently, that person was really busy. So, okay. So if you're looking at the amount of variation that your model is explaining in number of rearrests, you see is 2.67%. So now let's look at the predictors in the model. Remember, so these are unstandardized coefficients. So remember the null hypothesis with unstandardized coefficient is that the predictor is equal to 0. So here you see age. The null hypothesis is that age equal the coefficient for age equals 0. You see is significant. 0 isn't contained in the confidence intervals any. So what this tells you, the interpretations for both Poisson and negative binomial regression, for every unit increase in x, the expected log count, the expected log count of your outcome increases or decreases by whatever the value is. So similar to a ordinary least squared regression model, where say for every unit increase in x, y goes up by this amount, or goes down by this amount. It's the same thing here, but except we're talking about the expected log count, or the log of the expected counts. Let me interpret this for you. For every unit increase in age, the expected log, L-O-G, the expected log, like the natural log, the expected log count of the number of rearrests decreases by 0.3271335. So for every unit increase in age, the expected log count of the number of rearrests decreases, because it's a negative coefficient, decreases by 0.3271335. And like, what's the expected log count? And I'll get to a practical way to explain this, because similar to a multinomial logistic regression, everything, some of these unstandardized coefficients are hard to understand. Like with logistic regression, it was the log odds and everything. It's very difficult to interpret. But if you're practically looking at this, that's saying that the older you are, the less likely you are to be rearrested. It's saying as age goes up, the number of rearrests goes down. Gender. So here we're looking at male. The reference category is female here, since male is the one that's showing up here. Males are coded as 1 and females are 0 in the data. So it's also significant. So what that tells you is, so the expected log counts of rearrests for males is 1.27 units higher than the expected log counts of rearrests for females. I'll say that again. The expected log counts for males are 1.27 units higher than the expected log counts for females. But practically speaking, that's just saying because it's a positive coefficient, males are more likely to be rearrested than females. Convictions. So clearly some people were convicted in the data and some people were not convicted. You see is also significant. What this is telling you, because this is coded, those who are convicted on whatever date, on whatever charge, those who are convicted is coded as 1. Those who are not convicted are coded as 0. So what this is saying is that those convicted, so those convicted on any charge in the data, so the expected log count of rearrests for those convicted is 0.559 units lower than the expected log counts of rearrest for those who were not convicted. In other words, those who were convicted were less likely to be rearrested than those who were not convicted. Hope that makes sense. Your constant tells you the expected log counts. If all of your predictors are equal to 0, remember that's what the constant tells you. What's the value of the outcome? So in this case, the expected log count of the outcome. If all your coefficients are equal to 0, so 0 for gender is female, 0 for convicted means that they were not convicted. 0 for age has no value in there because our lowest age in the data is like 14 or 15 or something. So 0 has no value in the data unless you give it a value. If you center it or something like we talked about during class. If you can center any predictor around any value that you want to make the constant have some meaning here. So then the one second. Yeah, I did yours too. I sent you the stuff. Yeah, and I sent you the stuff. I sent you the taxes. I sent you the taxes to your email. Oh, taxes. I need some taxes. No, all right, there we go. Okay, I'm back. I was going to stop the video, but I can't figure out necessarily how to pause this. Um, so you had to deal with me for my break. So sorry about that. And I wasn't going to start over. So um, the ln alpha and alpha, these go hand in hand. This is pretty much just testing, but like, what is this? This is pretty much testing whether or not you should have did a Poisson, meaning the variance and the mean are equal. Um, Whether or not you should have did a Poisson or a negative binomial. So the 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 alpha is pretty much a value um, that if you did a Poisson model, meaning the variance and mean are equal, the Poisson model would mean a Poisson model would have, it pretty much constrains the alpha to 0 as the value. With a negative binomial, it allows the alpha to be greater than 0. Now, you're not going to interpret this or anything else. I'm just letting you know what these things are. So the alpha for this model is not 0 because it's allowed to be greater than 0, is 1.488541. If you take the natural log of that, so if you put in 1.488541 and then go to your calculator and press the ln button, which is the natural log, you'll come up with 0.3977967. Two sides of the same coin are these two. So what this test below here does, it tests to see whether or not to see whether or not alpha is equal to zero. That's the null hypothesis, is that alpha is equal to 0. If the alpha here was equal to 0, it's saying that the mean and the variance are equal, because alpha equals 0, because that's the assumption of a Poisson Poisson test. It's testing that assumption, and if it's equal to 0, your probability would be more than 0.05. So here it's saying this alpha, and after doing all of the tests, here's the value of that test, and it's significant, which means your alpha is not equal to 0. You reject that null hypothesis of alpha equal to 0. You accept the alternative hypothesis that the alpha is not equal to 0, which means a negative binomial is the appropriate test to use. So this is why it fit a Poisson model first. To test that against the negative binomial to see which one was the better one to actually use. So that was why they tested that at the very beginning. So this is just yet another way of testing to see which model is actually best for you. So that's how you interpret. That. Now, what's often the case in count models is something called an exposure factor. Like, what is an exposure factor? An exposure factor is recognizing that your outcome typically occurs within time or space. For example, it's not a matter of whether or not people were rearrested. That assumes that everybody was followed for the same period of time. Some people might have been rearrested, but maybe their time at risk was different. Meaning, somebody who was arrested 5 times over the course of 5 years might look different than somebody who was arrested 5 times over a matter of 7 days. Both arrested the same number of time, but their exposure was different. The time was different for each of those people. So being able to account for that. Or looking at some examples people use, for instance, if you're looking at the amount of income that somebody makes, but you don't take into account the period of time people actually been working in their job. You would expect somebody who's been working 20 years, just broadly speaking, will make more money than somebody who's been working for 1 year. So you'll want to account for that exposure based on the time that they've been working. So you'll come up with a factor in a model, an exposure of time working. Age can be that. If you're talking about, income, and I know it's not this clean, but just to illustrate the point, you expect older people to make more money than younger people, so age might be your exposure. If you look at the coronavirus, what that's going on now, New York has a significant number of cases compared to other states. Well, is it that, the exposure factor, for instance, can be the number of people in the state, how, in terms of the population, how dense the population is. New York as a state looks different than Maryland or California or Tennessee or Wyoming. So it's accounting for that, because it's not just about the numbers, it's the numbers based on the population of the state. So you want to be able to account for this exposure if you can. So again, if everybody is followed for the same period of time, if the population is the same, or the follow-up period is the same, or all these or the area is the same, then you don't really have an exposure factor in there. But I'm gonna tell you the difference that an exposure factor makes. So here we got number of rearrests. All of these things are the exact same, except here now we have the exposure as the time that people were at risk. The time at risk. So, because theoretically, the more time you had on the street to be at risk for reoffending, the more time you had to be rearrested. So all the syntax is the exact same, except afterwards, comma, exposure, and put risk time in parentheses. That's our exposure. Well, let's see what's different here and comparing the models. Tell you why exposure factors, if they're important for your study, see why they're important. You see the coefficient for age without the exposure was negative 0.327. With the exposure, negative 0.316. Almost the same. For male, 1.27 and significant. Here, 1.34 and significant. Slightly more significant, actually. But this is where it gets really important. Conviction. Without exposure, negative and significant. Very significant, actually. But once you account it for time at risk as an exposure, is no longer significant. Is no longer significant. Because theoretically, if people were convicted, they had less time on the street, which means they were less likely to be rearrested, which was this finding here, but was not taken into account. If you're not convicted, if you are convicted, that means you're on the street less, which is now accounted for in risk time. So now that you account for that, it's showing that conviction doesn't impact that. So this is the importance of, if it's appropriate, having an exposure factor in your model. And the interpretations are the exact same. So I just wanted to talk about the importance of having an exposure factor in there. It's not always appropriate for what you're doing, but sometimes it actually may be. And the final thing that I wanted to do for you was to convert these to um, a more interpretable model. And this is the incident rate ratio. Incident rate ratio. I actually just ran it. I didn't mean to, but it's negative binomial regression, comma IRR. You do this after you run your full model. You do this after you run your model. So then you got IRR. Standard error, significance, and everything else. This is kind of like an odds ratio to some extent. So incident rate, well, ratio is kind of like an odds ratio. Um, hence the ratio part of it. Is looking at the incidents, so the number of rearrests. It's a rate because technically it's done over a period of time. We're looking at the number of rearrests based on, within their time at risk. So it's really a rate also, even though it's not presented that way, it's really a rate. So it's the number of rearrests within this period of time, which makes it a rate. And it's a ratio because it's like an odds ratio, kind of like with logistic regression. It's a ratio there. And remember that a ratio tells you the likelihood of something occurring versus not. We talked about this on the first day of class, so I'm not really going to go over it again. But so that's where it's an incident rate, ratio, because all of those things are in there. So the incident rate ratio, pretty much, it can be interpreted as an odds ratio. So it's a difference between 1 and whatever the IRR is. So remember, unlike an unstandardized coefficient, where the null hypothesis that the unstandardized coefficient is equal to 0, that's the null. Remember, with incident rate ratios, odds ratios, all of those, is not based on 0, it's based on 1. Remember, 1 is that cutoff. Values above the 1 is a positive impact. Values below 1 is a negative impact. So here, you'll see the IRR is 0.72. So what this tells you is that for every unit increase in age, the rate of rearrest decreases by like 27.2%. So the difference between 1 and its value, I'm moving the decimal place over twice. So for every unit increase in age, the rate of rearrest decreases by about 27.2%. What this tells you for male, the rate of rearrest for males is about 283% higher than the rate of rearrest for females. So again, 1 from this value is 2.83, move the decimal place over 283%. Conviction, even though it's not significant, if you were interpreting this, the rate rearrest for those convicted is about 24% lower than the rate of rearrest for those who aren't convicted. But again, you see that it's not significant. 1 is contained in an interval here, which means that it could be 1, which means it's not significant. So that's the incident rate, a ratio. So again, you're talking about what's the rate of rearrest. You can do margins, but before we even go into margin, you see how these can be interpreted much more easily than expected log counts. Okay, you're talking about what's the rate of rearrest. So if, for instance, I want to say, okay, let's look at the let's look at the rate of rearrest for males versus females. So you got margins, gender, and keeping everything held at its means. Margins, gender, at means. Margins, gender, at means. So this is going to be looking at male and female, the predicted number of rearrests for males and females, holding everything else constant at its mean. Okay. So what this tells you is the rate, or not rate, sorry, that females are their predicted number of rearrests on average is 0.676052. The expected number of rearrests for males is 2.591371. If you looked at the percentage difference between them, in case you don't know how to come up with what's the percentage increase, like what's the difference in percentages for females and males, first thing you do is look at the difference between females and between males. Like what's it, now again, this isn't officially part of it, I'm just letting you know the link between how all of these things are actually done. And we're like, oh, females are expected to be rearrested 0.676052. Males on average, they're expected to be rearrested 2.591371 times. So you'd be like, what's that difference between females and males? So in order to find that, you look at the difference, like what's the difference in number between males and females? If you did that, I actually did the math, 1.91, you're not running anything, I'm just showing you here, 1.915319. That's the difference, 1.915319. That's the difference between females and males in terms of what their predictive value is. So, because again, I want to show you what's the increase from females to males in terms of this. Like how much greater, what percentage greater is males than females here. So the difference between them is 1.915319. If you divide that, so again, I'm showing you how do you find a percentage increase from one to the other. So you look at the difference between them, which is this number. If you then divide that by the original number, 0.676052, and you multiply that resulting number by 100 to make it 8%, what you get is 283.309%. So the difference between them divided by the original number, then multiply again by 100 just to get the percentage, 283%. Well, look at here, the incident rate ratio. Males have a higher rate of rearrests than females of 283.309%. That's what this is. So you can see how the incident rate ratio and predictions are linked. If you're keeping everything at its mean, like, oh, just look at males and women, and males and female. Okay, remember, all a model is say, all right, what's the average effect for gender holding age and conviction constant? So here we held it constant. We just held it at its means. The difference. So you see that males, if you're looking at the difference in males and females in terms of the rate of reoffending, you see it's a 283% difference between them. And you can come up with predictions for any value for stuff that we've done in class. You know how to do those things. I'm not going to bore you and everything else. So I hope this helped. I hope you enjoyed it. Thank you very much. And I will post the homework and all those good things. Have a good night.